Good morning, everyone. This is Yas Kansal, and I've been working in Suho for over a year now. So, today we are going to talk about music modeling in town planning, like how we can include music modeling in town planning purpose. So, starting with Introduction to Music, it's model for urban stormwater improvement conceptualization. That is a software that helps developers and planners to devise their water sensitive urban design and integrated water cycle management capability to manage urban stormwater. Thousands of professionals working on stormwater across Australia use music. It is developed by Music by eWater. Their head office is in Canberra, and now they have released few versions of music that we'll be working on at later stages. So first of all, we need to know what is the difference between Storm and Music tool. As we all are aware, both of these can be used in BESS assessments depending on the scale of the project. So what is the difference? Music is applicable for larger sites for more than 1000 square meters, whereas Storm is applicable for smaller sites which is less than 1000 square meters. Music focuses on quality by treating the water with four elements. Storm provides a general combined percentage that is required for the treatment. Music in music we have many more options available for treatment, while in Storm we just have few options available for treatment. Music is more of a time consuming method, but Storm doesn't involve much time in it. So going forward, what does music do? Music lets us conceptually choose appropriate sizes for water, stormwater infrastructure options. Music can model a wide range of treatment devices to identify the best way to capture and reuse stormwater runoff and remove its contaminants and reduce runoff frequency. We can apply music at a range of catchment scales. By using it to compare alternative designs, you can confidently decide on those that give the best outcomes in cost as well as hydrology and receiving water quality. Going further, so we need to know certain standards before doing music modeling so that we can adhere to those standards. So the first one is the Urban Stormwater Best Practice Environmental Management Guidelines, that is also known as BPEMG as a short form, that provide a toolbox to meet the needs of those planning, designing, and on managing urban lands uses of stormwater systems. It is now compulsory under the Victoria planning provisions for many types of residential, industrial, commercial, and public developments to design and manage urban stormwater management systems to meet the current BPEMG objectives. So, what are the results? As we discussed earlier, in Storm, we get the 100 percentage or percentage like that to get the full results. Here, the results are suspended solids, that is 80% retention of the typical urban annual load. Total phosphorus, that is 45% of the typical urban annual load. Total nitrogen, that is 45% retention of the typical urban annual load. Liter is 70%. But flows maintains discharge for 1.5 ARI at a pre-development levels. What is ARI? ARI is average recurrence interval that is already calculated in music. So we don't have to worry about that while modeling in music software. What are the music objectives? So it can simulate stormwater flows and retention from large scale to suburban scale. It means we can either design a small scale property or it can go to a full city. It can model pollutants including suspended solids, total phosphorus, total nitrogen, and estimate the impacts of various treatment options. It can model water balance. It can compare the water quantity, quality, and cost versus benefit objectives achieved by alternative treatment range scenarios. And in the last, it can plan entire stormwater systems. What is the first step while modeling the music? It's the rainfall templates. So here is an example that how we should model the rainfall templates. First of all, we need to determine the project location. As we can see image on the right hand side, Melbourne's map is divided into different zones, and each zone and each color has different rainfall template. Supposedly my project lies in Essendon or something, then I have to choose Melbourne Airport rainfall template which is marked in yellow color. Either we can create our own rainfall template or we can use existing templates provided by Melbourne Water that has been discussed now. So rainfall template selection. First of all, climate data including rainfall and evapotranspiration are essential inputs to music. As we can see image on the right hand side, the rainfall data where Canberra airport has been selected with 6 mm rainfall. We can browse that and consider our area or whatever area you want to model in. It can be Perth, Brisbane, whatever. Then after selecting that, we have to go with potential evapotranspiration data. Where monthly average values are there, you have to put on details, click on details, and when you click on details, you have to select the same area file so that rainfall data and evapotranspiration data are from the same area. Then you have to put on the template time step that has to be on 6 minute interval. And if you intend to model without Melbourne water provided rainfall templates, data is available from Bureau of Meteorology, which we also known as BOM, at a 6 minute time in step for a number of gauges across Melbourne's water service areas. So, the other important part. What are the catchment areas? Urban nodes are mostly used for modeling purposes to represent existing urban new development and parkland areas. So forest nodes in music are only recommended for use when representing old growth or well-established forested areas. Source nodes can be split into surface types like roofs or roads, etc., which we are going to discuss in the next slides. So source nodes are catchment areas. Catchment areas are known as source nodes in music modeling. So we have five types: urban, agricultural, forest, user-defined, and imported data. As we all discussed, we normally use urban road in music while working for town planning. So we have two images on the right hand side showing the properties of the urban node. So area is given in hectares. On the left hand side, left image, we can see area is given in hectares. So we'll convert it to hectares from meters, then put it over there. Then zoning surface type is shown as mixed. If it's hard surface like roof, then we'll select roof, or it's concrete pavement or something, we'll select it as sealed road or unsealed road accordingly. So talking about the imperviousness is marked in black strip, while the perviousness is in green strip. So if we know like our roof is 100% impervious, so we'll drag that black strip to the end to the 100%. So it should be good to go. Then we have to click on next button. Then comes with the rainfall runoff parameters that we don't have to touch in music at this stage. And then we'll just finish it off and our urban node will be good to use. So then comes the treatment devices, rainwater tanks. These are domestic water stores that enable roof runoff to be captured and used. Contaminants can either settle in tank or are removed when the water is used on a garden. Tanks can reduce stormwater flows and help to contract the increase in impervious area that urbanization brings. They also provide an alternative water supply, which we are going to discuss in the next slide. So rainwater tanks. How do we calculate? The right hand side two images show the properties of the rainwater tank, that how we should input the properties or the values so that we can use it for the modeling purpose. First of all, we need to determine the capacity. As we can see in the inlet property, we don't need to touch it. Number of tanks we can put accordingly. Total tank properties. First is volume below overflow pipe. That is the volume that we want to use. So supposedly it's 10 kiloliters, then its depth above overflow meters, that is 20 centimeters, that should be standard. Surface area, how do we do that? As we know, the surface area of a sphere is pi r square meters. So we'll determine, like, if I have a 10 kiloliter tank, I'll have a look online with the 10 kiloliter tank dimensions and calculate the surface area and put it over here. Initial volume should be same as the volume below overflow pipe. So overflow pipe diameter is calculated automatically unless we have specific requirements. So at this stage, this part is only used for detention tank because we haven't added reuse properties. If we want to use it for reuse, then we'll click on reuse button. Then you can check on use stored water for irrigation or other purpose shown on the next image. Max drawdown height is automatically calculated. We can calculate the annual demand and daily demand. Like daily demand is given to us automatically. Annual demand can be calculated by multiplying the daily demand into number of working days. Like in residential, it can be like every day, but in Commercial property, it's like 5 days a week, and in Australia, we can generally assume 251 days of working in a year. So we can multiply by 251 and put the values over there. So it should be good to go. So in the next part, we are going to discuss the bioretention systems, that is also known as rain gardens. These are vegetated stormwater filtration systems that use a soil or sand-based filtration medium to remove particulates and soluble contaminants. The system may be lined or unlined and may or may not have an underdrain. In music, based on significant extra data and research, bioretention nodes take better account of the characteristics of the filter media and vegetation. Music users can now more accurately design or represent a variety of different bioretention systems. How do we model bioretention systems? As we can see, the properties of bioretention system on the image. Inlet properties has to be standard. Storage properties is the extended retention depth. It has to be 300 mm, so that should be there. Normally it's given 200 mm, you can go with 300 mm. Surface area is like the size of the rain garden we want to provide. Then the filter area should be 85% of the surface area, because normally when we are designing a rain garden, or in practicality, some part of the rain garden is workable while rest is not. So 85% will actually work as a rain garden. So that's why we have to put the filter area to be 85%. Rest of the properties like unlined filter media, saturated hydraulic conductivity, filter depth, content of the filter media, and etc. has to be default. Lining properties, it's baseline or not. While in town planning, we are not aware which kind of rain garden will be used. So we'll say no, and we'll check on the vegetated with effective nutrient removal paths. Outlet properties is going to be standard. We'll discuss in brief about other treatment devices. Then is the buffer strip. These are the strips of vegetated land beside a road, and which are effective in the removal of coarse and medium-sized suspended particles. They provide good pre-treatment prior to a bioretention system or other vegetated treatment measures. So basically, it's like we can put a buffer strip in a slope before the rain garden, and then it can reduce the load of the rain garden when there's excess of water coming. So normally these are not used in small scale projects. So it's like generally used when we have very big projects and a very big rain garden is there, and we still have a very big slope that is carrying a lot of water to the rain garden. So vegetated swales, these are open channels that use vegetation to primarily remove suspended solids. These are subject to high flows. They rely on shallow slopes and the density and the height of vegetation to work well. Then others are ponds and sedimentation bases. These are open water bodies that act as temporary stores to allow the settling of suspended solids. They can include ornamental ponds but usually lack vegetation. Reuse of the water is an option in them. Then we have wetlands. These are heavily vegetated water bodies. These are physical, chemical, and biological processes that they facilitate to remove fine suspended sediment and soluble and insoluble contaminants. Wetlands are commonly used as end-of-pipe measures, but recent research shows that they also work well earlier on. Music can also model reuse of the water in wetlands permanent pool. Treatment devices. Detention basin. It assists in stormwater pre-flow management. As we can see image on the right hand side, what it does is we can see the riprap. So it's a seepage that we allow in the basin so that excess flow can be leaked to other parts. Gross pollutant traps, these are mesh-like devices that are designed to remove floating and suspended rubbish and debris above 5 mm in size. Many are proprietary of the shelf items. We are going to discuss about them in next slides. Infiltration systems, these are unvegetated infiltration systems that are used for removing contaminants which have no underdrain. Music V4 offers a great enhanced infiltration modeling capacity to account for horizontal flows from storage and allow for changes in flow and with depth. There is greater flexibility to model systems with line sensor based. Treatment nodes. So no treatment can be attributed to a GPT or a generic treatment unless it is supported by reliable studies where reliable and locally representative data is available. Gross pollutant and sediment treatment may be attributed to a GPT or generic treatment. How? As we can see images on the right hand side. First one depicts properties of gross pollutant trap. The other one depicts properties of generic treatment node. How does gross pollutant trap work? Supposedly, there's a product that works as a GPT. We need to know which element it will target. Like we have four elements: gross pollutants, total suspended solids, phosphorus, and total nitrogen. So we click on each one and see how much percentage is going to target. For this one, we need to get data from the relevant supplier. And like for input, if we have 50% and we know that gross pollutants is going to be worked as 50% in this part. So we'll reduce the 50% and output should be 25. So this is how we'll calculate the GPT and then we'll click on the finish button to use that. Similar thing can be done in generic treatment road. We need to know the product that we are going to use, like humiceptors. They have different properties and like 80% in gross pollutants and phosphorus. So we can reduce phosphorus by 80% by clicking on total phosphorus area, and inflow and outflow can be managed accordingly. Then this button and this treatment device is also used, but we have to make sure we get the relevant data from the relevant supplier. So how to do a typical music modeling? We should start with adding existing rainfall template that we discussed in the initial slides, or we can make a template of our own. Then we add the background image from the drawing. We add nodes and catchment areas. Then we add the treatment methods to the catchment areas. Then we link it with the drainage system that is shown in blue lines. Then we run the model and we get the results. Here's an example of music modeling where we can see a development with hard surfaces and landscape, how we can do it. So we can see the level 1 outdoor play area is connected to a bioretention that is going to the receiving node. Roof is directly going to the rainwater tank and then to the receiving node, and hardscape is not treated, that is going to the receiving node directly. When we click the run button, we get the results which is shown in the image on the right hand side. We can see the suspended solids percentage reduction is 94.9, which is more than 80%. Phosphorus is 71.4, which is more than 45%. Total nitrogen is 81.4, which is more than 45% as well. Gross pollutants is 98.9, which is more than 70%. So we can use these results in BESS, and then we can say that our music modeling is in compliance with the water requirements of the council. Considerations for town planning, like many of the councils nowadays have like set criteria that what treatment devices should be considered for water management. First of all is a rainwater tank. So it's easy to use and it has retention properties, it can be reused, so that's why rainwater tank is the first option. Second is the permeable surface. Permeable surfaces are the surfaces that allow water to seep in through. So nowadays different construction options are available for permeable surfaces, like we can use them in parking or wherever we want. Then is the rain garden. The only issue with the rain garden is the maintenance properties, and sometimes when the site dimensions or the site constraints are too much, so then it's difficult to put rain garden in the property, or we need a good slope for the rain garden to work properly as well. Otherwise, for music, I would say rain garden provides really good results and it really takes off the elements and provides us good results for the effective nutrients. So now at the end, anyone has any questions, you can type in the chat and I'll try to answer all of those. Questions, anyone? Okay, so you can log into other webinars and you can send us a query through